Okay, I think I just turned on the recording. Let me just check, make sure that it agrees that it's on. Yep, okay, it agrees that it's on. Okay, hello everybody. Welcome to the engineering class. Before I begin, does anybody have any questions about anything, how the class is running? We're going to be talking about the homework and the online quiz in just a minute. So other than that, questions about how the class is running, questions about AIMS in general? I'm saying no. How about the rest of you? Give me a yay or nay. Also, this helps confirm that you can actually hear me. I think it's important that I need to know if you can actually hear me. Okay, so yes, yay, okay, good. All right, well, let's go ahead and get started then. Okay, all right, so first, I know that some of you have turned in the homework. Many of you, in fact, have turned in the homework, but there's still a fair number of you who have not yet turned in the homework. And because of the way we have to run things now with the shutdown, it's really important that you do the homework, get it in on time. So I am instituting this new policy, which you see on the screen right now. Everyone is now allowed 2 and only 2 late homework assignments. If you have any more than that, you just take a 0 on it. So get the stuff in by the deadline, and Canvas will tell you what the deadline is. So Marshall's saying, uh-oh, yep. Well, this is from today going forward. So what I'm just, sometimes I scare myself on being such a nice guy. So what I'm going to do is, if you didn't turn in today's homework on time, I'll still accept that one, and I won't count that as one of your late ones. But from today forward going on, 2 and only 2 late homework assignments. After that, 0. Okay, let's talk about last time's test. All right, so let's see. All right, so if you missed question number 1, I seriously worry about you. That was an easy gimme. And by the way, note what color I'm wearing right now. Now, I'm not saying that's going to be a question on today's test, but it's worth noting anyway. Okay. All right, question number 2. What is a series circuit? All right, so you can see the correct choice down here, one where all of the current has to pass through all of the resistors. And the best way to help you understand that is to compare it with something that is not a series circuit. So what you see right here, the circuit on the right is a series circuit because all the electricity that comes out of the battery and flows along here, it all has to go through that first resistor, and then after it comes out of there, it all has to go through the second one and then through the third one. So it has to go through each one in the series in order. That's what makes a series circuit a series circuit. Now, if you look over on the left side, you can see that what I just said is not true for this thing on the left. The electricity that comes out of the battery has a couple different options. It can go through R1 if it wants to, but it doesn't have to. It could come over here and go through R2, or it could go through R3. And so actually what happens is that some of the electricity goes through R1, some through R2, and some through R3. So this is a very, very different kind of a circuit. All of the mathematics for how everything works is very different. It's not my intention right now to talk about parallel circuits in this class. If you want to know about parallel circuits, I recommend that you take my electronics class. We go over it in gruesome detail in the electronics class. In this class, we're going to stick with just series circuits. Makes things a whole lot easier. So David is saying yay. But David, you should be an expert on parallel circuits. Okay, question number 3. All right, so we've got a simple circuit, 1 battery, 1 resistor. So all we have to do is use Ohm's law on this one. Hopefully, really, really simple. So the answer that we get on the calculator is 0.019 amps. And so that's the choice right here. Now on question number 4, okay, I've done 2 things different. One is I added on another resistor, so we now have 2 resistors, but they're in series, so it's really simple. And the other thing is, this time when I expressed my answer, I didn't express it in amps. I expressed it in milliamps. So the number on my calculator is 0.018, but I chose to express that in terms of milliamps, not amps. You guys have got to become very, very familiar with converting units. So in fact, tell you what, let's do. Let's talk about unit conversion. I promise you, in all your science classes that you take from now on, if you don't know unit conversion, you're going to be in big trouble. In chemistry, boy, you got to convert units. In physics, you got to convert units. In biology, Miss Aho doesn't do a lot of calculations, so it's not so big there. But when you get into chemistry and physics, you got to be really good at unit conversions. So what you're seeing right now is a copy of a poster that I have in my room, and many of the other science teachers have it in their rooms too. This is the Ames method. Now, what happened was I used to call this the Hendricks method, but the other science teachers, they all complained this is, hey, wait a minute, that's the same method we use too. So I said, okay, I'll call it the Ames method. But then other teachers from other schools, they saw that and they said, hey, wait a minute, that's the method that we use too. So, hey, I'm going to call it the Ames method, even though it's pretty much the method that everybody else uses too. If you use this method, you will never go wrong. Okay, so let's do an example here. Okay, so first step, we want to write down the given quantity with the given units. So let's suppose we've done the calculations and the answer on our calculator says is 0.018 amps. But we get awful tired of saying 0.018. So we want to convert it into milliamps or something where we don't have to say 0.0, all the time in front of it. I should have patented it when I had the chance. Yeah, you're right. Only trouble is I don't think they would have granted the patent because other people have been using it ahead of me. Okay, so anyway, we've got this number here, 0.018, but we want to express it in other units. Okay, so step number one in the Ames method. Okay, so we write down the number as you see with the units. Step number two, we write down the conversion factor we need. So let's say we want to convert it into milliamps. So we say to ourselves, if only I knew how many milliamps was equal to an amp. Well, you go and you look it up. All right, and so right there, you see the conversion factor. So I like to write it off on the side there. So 1 amp is 1,000 milliamps. Okay, let's move to step 3 now. Step 3 says, let's take the number that we just wrote, and next to it, we're going to put some parentheses and a horizontal line. And then what goes in there? Well, that's where these guys go. So the conversion factor here, one of them goes on top, one of them goes on bottom. And we got a 50-50 chance if we were to just totally guess. We got a 50-50 chance we might get it right. Now, in this case here, you can see I put amps on the bottom, milliamps on the top. Now, I had a reason for doing it that way because I knew that I've got amps over here. I trust you can all see my arrow. Okay, good. So I've got amps over here, and I want them to cancel out, so that's why I put amps on the bottom. Okay, so I know what I need to do is I need to take 0.018, I need to multiply it by 1,000. But just to be sure, here's another part of the Ames method, and this is something that people sometimes forget. Students sometimes forget this, and this is really important. You have to cross out the units. And now you might say, well, why? Well, wait a second, and you're going to find out. Okay. All right. So we've crossed out the units. So you notice the amps are all gone now, and I've moved, and the only thing I'm left with is milliamps. And so now I know that in order to get my answer, I have to take 0.018, multiply it by 1,000, and life is good. Okay, so let's get back to the question of what if we don't follow the Ames method? Because I see this all the time. I see students say, well, I know what to do. I use multiply by 1,000. Wait a minute. Or is it subtract by 1,000? I can't remember for sure. If you follow the Ames method, you will never go wrong. Okay, so let's say that you're one of those people that says, I know what to do, just divide by 1,000. Well, is it? Okay, if you had followed the Ames method, you would have known, because if you had followed the Ames method, you would have taken the number with the units, okay, not just the number by itself. Okay, this is what students like to do, but the Ames method forces you write the units. Okay, so we got amps here, amps there, And now the part that I said a minute ago that students like to forget, crossing out the units, okay? When you go to cross out the units, you say, oh, wait a minute, I got amps up here and milliamps down there. Whoa, they don't cross out, something's wrong. So now you know you made a mistake. You know that you shouldn't have divided by 1,000, you should have multiplied by 1,000. And thanks to the fact that you followed the Ames method, you've discovered your mistake, and you can go back and you can correct it, okay? So I want everybody to get really good at the Ames method for unit conversions. In the quiz that we're going to take today, there's a couple questions there where you have to do some unit conversions. And if you follow the Ames method, you will be fine. If you don't, maybe you will, maybe you won't. So let's be safe. Let's follow the Ames method. Okay. All right. Question number 5. All right. So we've got a voltage divider. I've given you the values. I've asked you to do the calculations. I get 4.8. I'd like to hear from you guys. What do you think about that? Did you get that same answer? If not, do you understand why not? Does anybody want me to go over how I got that number? Because if you don't have ask questions, I'm going to assume you don't have any, and we'll just move on. I'll give you a second here. I'll wait. So let me know. Can you guys understand where I got that 4.8 from? Not seen. Okay, good. Okay, seeing lots of yeses. Okay. All right, good. Okay, good. All right, so I do have a slide here that I talked a little bit about it. So I won't dwell on this, but just in case you have a question, here's the slide. Here are the numbers. Here how I got it. But I'm not going to dwell on it because you guys are saying that you understand it. So there we go. Okay. So question number 6. Again, if you have questions, I'll gladly go over it. The answer here is 580. So tell you what, I did prepare something just in case you do have questions. So what I did was I said, okay, I know that I want V out to be 3.3. And I know what R2 is because over here it says R2 is 120. So I know what the voltage across R2 is. And so that means I know what the current through R2 is. And if I know what the current through R2 is, I know it's the same current through R1 because it's a series circuit. Now, some of you say, well, wait a minute, the fact that I connected V out here, that gives the electricity another path to flow through. And if I did use that to drive, if I did use V out in order to drive some other device, that would be the case. But we're going to be using it as an input to the Arduino, where the Arduino is just going to read the voltage. It's not going to actually use any current. It's just going to read the voltage. So it is true that for us, the current through R2 and the current through R1 are going to be the same. So Danny is saying that, yeah, if we wanted to account for that, we could. But in this class, we're gonna assume that the whatever we hook up to V out is going to pull so little current that the current through R1 is equal to R2. Now, if you want to do more advanced things, take my electronics class. Okay, so we know now that the current through R1 is a 0.015 amps, which is 15 milliamps. We know the same current must be going through R2. And so then we say, okay, so now we know the current through R2. And what about the voltage? Well, okay, the total voltage was 12. And we know that the voltage across R2 here was 3.3. So whatever is left over, that must be the voltage that's across R1, so 8.7. So now we know the voltage across it, we know the current through it. So now if we take Ohm's law and do a little bit of algebra, which I trust you guys are good at algebra. Okay, so I can take Ohm's law and multiply both sides by R, divide both sides by I. So I get R equals V over I. So I know what V is, I know what I is. Therefore, I calculate R as 580. So I hope this is cool. Now, those of you who watched the Khan Academy video, you saw that they do it a different way. They do it the way that Luke wanted to do it. Remember what last time Luke came on with his voice and he explained a method that was math intensive? It's a perfectly good method. If you're good at math, if you're comfortable with math, Luke's method, which is the same as the Khan Academy method, is a great way to do it. I like the Hendricks method here because you don't really have to do very much math. Just kind of logically think your way through it. And you don't have to use the complicated formula. I mean, it's not that complicated, but you don't have to use any complicated formulas. It follows straight out. Okay, so questions on that? Yes, no. I'll wait a sec till I see some questions. Somebody type something in. No. Okay, good. What's that? Brug? Okay, all right. We're going to go ahead and move on then. All right, so that's it for the quiz. So just by way of reminding everybody, the reason we're doing this, all this with the voltage dividers, is because we've decided that our Rev1 burglar alarm is not going to be financially successful because it uses the solar panel, which is pretty expensive. And so our competition, they have figured out that if they use a photoresistor instead of a photo panel, they can sell it for a whole lot cheaper because the photoresistors, if you buy them in bulk, cost about a penny a piece, where these photo panels can cost you $1 or more. Okay, so they can undercut us. But the thing about the photoresistors is if you just take a photoresistor and you just plug it into the Arduino, where'd my Arduino go? Oh, here we go. Okay, so if you just take the photoresistor and you just plug it right straight into the Arduino, the same way that we plugged in the photo cell, the solar cell, it's not going to work because the Arduino reads voltage. Now, solar panels do put out voltage. So when we plugged in, that worked great. But photoresistors, they do not put out voltage. So if we just plug it in, it's not going to work. Okay, so what we have to do is we have to create a circuit that's a voltage divider circuit, and then use the output that we in our voltage divider we call it V out. We use V out as the input voltage to the Arduino. Then we can use the photoresistor and save ourselves some money. Okay. All right. So here is a picture of a photoresistor, and the actual photoresistor. Okay, now I've got it connected up to some leads here. You're going to find out in a minute why I did that. Okay, so here's the actual photoresistor. Okay, and so the neat thing about photoresistors, one neat thing about them, is that the resistance changes. So if it's in strong light, the resistance is only a few hundred ohms. Like for instance, let me get my light here. Okay, all right. So I'm going to take the photoresistor, I'm going to hold it to the light, and let me turn this on. Okay, so this is a multimeter. It can measure resistance, measure voltage, measure current. Here's one, you guys, I really feel bad for you. You are getting cheated so much. If we were able to hold class at school, you guys would get to use these photoresistors, these multimeters, and you would actually be able to build things. Using multimeters is a really important skill. That light's pretty bright. Let's turn that on. Using multimeters and photoresistors and Arduinos and all these good things, you really got to do hands-on. And you guys are getting so cheated by the fact that you can't do hands-on. But hey, what you gonna do? Okay, so I've connected the photoresistor to my multimeter. Let's get this light back here. Okay, so when I hold this to the light and you look on the multimeter, you see we're getting, let's see. Okay, so we're getting about 500, depending on how close I hold it. If I back it off, it goes down. If I go closer, wait a minute. Okay, if I back it off, it goes up. Okay, you go closer, it goes down. Okay, so this is reading how many ohms of resistance we have. So look what happens when I put my finger over it. So now it's in darkness. Okay, now some of you are going to say, well, the number went down. It went from 500 down to 3 point something. But did it? If you look right here, you'll see that when I put my finger over it, a little K appeared. Let me get it. Okay. So that 3 point something that you're seeing, that's 3 point something kilo ohms. not 3 point something ohms, it's 3 point something kilo ohms. Okay, so when the light is on it, the photoresistor has less resistance. And then as I move it away, the resistance goes up. And when I cover it up completely, the resistance goes way up so that the resistance is measured in thousands of ohms. And actually, every photoresistor is a little different. A typical photoresistor, when you completely cover it up, the resistance is going to be actually measured more in tens of thousands of ohms. Okay? Everyone's a little bit different. Okay, so that's photoresistors. That's how they work. So what we're going to do now is we're going to take a photoresistor and we're going to use it as one of the resistors in our voltage divider. So that way, when the resistance changes, the V out here, you guys okay? So when the light changes and the resistance of the photoresistor changes, then V out is going to change as well. And so we can know that the burglar has come. Okay, so what you see right here, I've got the photoresistor in place of R1, okay? Now, schematically, this is the way that it's usually shown. When you have a resistor with a little arrow on it like that, what that means is that it's a variable resistor. It's a resistor that the resistance can change. Okay, so we could put the photoresistor in place of R1, but we don't have to. We could also put it in place of R2. And would the circuit behave the same way? Interesting. The answer to that question is no, it will not. Okay. All right, so let's do a problem here. And by the way, your homework tonight is going to be the quiz. And I'm going to give you 2 days to do the quiz. Oh, let me get that. That light is really bright. Okay. Now I don't have that bright light in my eyes. So your homework tonight is going to be the quiz. And the questions are going to be a little bit more than just what color is my shirt. You're going to have to do problems like the one that you're seeing right now. So we're going to assume that we have a photoresistor where when it's light, okay, can you see? Okay, so there's the arrow. Okay, so when it's light, the resistance is 500 ohms. And in the darkness, the resistance goes up to 10,000 ohms. And we're going to assume that we're using it here in R2. So it's like this. So this is where we've hooked it up. So this is the schematic for it. Okay, so we're also going to assume that we're using a 10,000 ohm resistor for R1. We could use another one. And in fact, in a few minutes, we're going to talk about the implications of using a different one. For right now, I've just randomly chosen, I'm going to use a 10,000 ohm resistor for R1. Okay, now what about V in? What's that going to be? Well, we are going to be using the Arduino not only to read the sensor, but the Arduino is also going to provide the voltage for us. So the Arduino down here has some voltage pins where it puts out a constant voltage that we can use as the V-in for our voltage divider. So what we're going to do is we're going to hook it up so that the input voltage is the 5-volt pin on the Arduino. All right. So there we have our input is 5 volts, and we know R1, and we've got R2 whose resistance varies. Okay, so make sure you know how to do this. Everybody follow along here carefully. Okay, so the question then is, what will V out be when the photoresistor sees light? Remember the way we did the burglar alarm before was we have a light that's shining into the sensor, and if the burglar comes, he blocks the light. But we're going to assume that the burglar is not there. So the photoresistor is seeing the light. So I want to know, what will the voltage on the output be, because that's going to be the input to my burglar alarm program. Okay, so how do we go about doing that? Well, okay, so I have calculated here that it's 0.24 volts. How did I get that? Well, exactly the same way that we did with the problems we did in the homework. Okay. Actually, should we talk about how we did that? Do you guys want me to go over how I got 0.24 volts? Or do you trust that since you did the homework and you claim that you understood the homework, that we don't need to? So give me some feedback here, guys. Do you want to know how I got 0.24 volts? Yes, you do want to? Okay. Okay, so some are saying yes, some are saying no. Okay, so I'll do it really quickly here. Okay, so I'm switching modes here. Okay, so I know that my total resistance is, so let's come over here. And let's see, let me get rid of a couple of things here. My screen has some stuff here that's blocking my view here. Okay. All right, so we know that the total resistance is going to be 10,000 plus whatever the resistance is of the photoresistor when it's seeing light, which we've set up here as 500. Okay, so the total resistance then is going to be 10,500. And tell you what, let me change that. And just a second here. Let me make that so it fills with white. And also let's make it so it jumps out at you. And let's make the font a little bit bigger. Okay. They're going. And let's spell resistance right. Okay, so we know the total resistance, if the photoresistor is seeing light, the total resistance is 10,500. Okay, so that means we can figure out what the current is. The current, which is equal to V over R, is going to equal 5 divided by 10,500. Okay, and let's see, what did that work out to be? So 5 divided by 10,500. Okay, so I get that the total current is 0.000476. Okay, so now I want to know what is the resistance across the photoresistor, because that's my V out. So if I do a little bit of algebra here to Ohm's law, I can get that V equals I times R. Okay, so I just calculated what I was. So it's 0.000476 times whatever the resistance is. Now R2 here is my photoresistor, so that's 500, right? So I take my last answer, multiply it by 500, and I get 0.238 volts. 0.238, which I have rounded off because I only want to use two significant figures. So my answer there is 0.24. Okay, so I trust everybody's good with that now. Okay, so Luke is suggesting a slightly cooler simulator there. So, okay, I'm going to, I've got several electronics simulators that I've used too. I will look at those that you've got. I've been toying with the idea of whether I should use electrical circuit simulators. In my electronics class, where we go to in great detail, then that would definitely be the way I would do it. But in this class, I'm not planning to go into electronics much more than what we've already done. I think this voltage divider is about all we're going to do. So David, I completely agree. The best one is just having an Arduino. Okay, so let's move on now. Let's go back here. Let me go back into display mode here. Let's go on to our next slide. Okay, so we've decided that if the burglar is there, V out is going to be 0.24 volts. Or I'm sorry, if the burglar is not there. If the burglar is not there. So what if the burglar is there? So here's the light coming here, and then the burglar comes, the burglar blocking the light. So what will the output voltage be if the burglar is there? Tell you what I think I'm going to do. I'm going to stop for a sec. I want you guys to figure it out. Prove to me that you actually know your stuff. Okay, so I've done it once now, where the resistance was 500 ohms. Now let's say the resistance has changed to 10,000 ohms. I'm going to sit back and I'm going to relax while you guys get out your calculators, and let's see who can get the answer first here. Okay, so Luke is saying 2.5. That was good and fast. Do we have anybody second that motion, or do we have anybody opposed to it? Okay, Eve is agreeing 2.5. Caden is agreeing. Okay, looks like everybody's agreeing that it's 2.5. Let's see what I did when I did this. Okay, hey, what do you know? I get the same one. All right, no wig today. All right, so the range then between the input voltages to the Arduino then is it's going to range from 0.24 volts up to 2.5 volts. So that's basically a range, a factor of 10 different. So that's pretty good. We can work with that. All right, now, as you see here, I'm saying be careful, because if you make a bad choice for R1, then the range will not be as good as what we got before. And let's work an example here. So let's suppose, again, I just randomly picked one. Let's say instead of using a 10,000 ohm resistor, what if I only have a 100 ohm resistor? Okay, what is that going to do to the range of values? Okay, so everybody take a minute. And so let's see, let me do this real quick. Okay, good. I was worried that I had put the answer on that next slide. So I see that I haven't, so that's good. Okay, so I want you guys to take a minute and figure out, okay, so now what will the voltage be? What will the out be if the burglar is not present? So the photoresistor is seeing light now. What will be the output voltage from our voltage divider now? Okay, Luke is saying the voltage drop will always be 5. Go back and redo that one, Luke. It's not going to be always 5. I'll sit back and wait. Oh, I see. You were answering Caden's question. All right, sorry about that. Okay, yeah. So yeah, I should look more carefully. I wasn't watching. I didn't see Caden's question. So yeah, Caden, and that's why you have to have 2 resistors. Luke is absolutely right. If you didn't have R1, the voltage would always be 5, and whether the burglar is there or whether he's not. So it'd be a pretty useless burglar alarm. So Luke, thank you for answering Caden's question for me. All right, so Eve is saying that if the light is on, we're going to get 0.0495 volts. Does anybody agree with that or disagree with that? I need to see a couple more. Oh, no, Luke, give me an answer. Don't give it to me like that. Give me a number as an answer. I need to see a couple numbers here. Wait, I think that's the light is off. Yeah, okay. Good catch, Steve. I was wondering if you were going to notice that. Okay, Simon, true statement, but not particularly helpful. You're going to have to be a little bit more specific than that. Come on, somebody give me an answer. Okay, so 0.245, 4.15. Oh, this is interesting. I'm seeing lots of different answers this time. So apparently you guys did not understand voltage dividers as well as you thought they were. Okay, so now I'm starting to see the same, oops. I was seeing the same answer. Now all of a sudden I'm not anymore. Okay, so we are seeing some different answers here. I'm gonna pause. I want everybody to go back and do it again. Do it a second time. Let's see what you get out. Okay. So we're seeing light so that the photoresistor is 500 ohms. The other resistor R1 is 100 ohms. I want everybody to go back and do it again. When I see that many answers, that tells me that we don't understand things as well as we want. Let's see what you come up with again. Yeah, I see people are getting confused about light versus dark. So if you look up on the top left hand of the screen, it specifically says we're seeing light. Okay, so that means the photoresistor has a value of 500 ohms. So the total resistance is going to be 600 ohms. Okay, so now, all right. Okay, it looks like everybody's saying 4.17 now. Okay, let's see what I got when I did it. Yes, that's what I got too. I rounded it off to 4.2, but my calculator said 4.17, just like yours did. Okay, but I'm rounding it off to two significant figures. Okay, so now what if the photoresistor is in darkness? Some of you have already done that, but the rest of you, go ahead, take a minute. I want everybody to calculate what will V out be if the photoresistor is in darkness. I'll give you a minute for that. I'll sit back. So while you're doing, I'll ramble on here. Okay, so I'm seeing 0.05. Okay, so if it's in darkness, that means that the resistance is 10,000 ohms. So the total resistance is going to be 10,100. So what does that mean the current would be? And once you know the current, you multiply that by 10,000. Okay, so I'm seeing two people are claiming it's 0.05. Let's get one more person. I want one more person to chime in here. Okay, good. All right, we got one more person. And let's see if I agree. Whoa, I did not agree. Ah, interesting. Okay, so what went wrong, guys? So Luke is agreeing with me. That's good. Okay, so what went wrong? Well, let's calculate it again. Okay, so if the photoresistor is in darkness, the total resistance is 10,000, or its resistance is 10,000. So the total resistance is 10,100. So what is the current going to be? The current is going to be 5 divided by 10,100. Oops, I guess it helps if you turn on the calculator first. Huh? Okay, so 5 divided by 10,100. Okay, so I get that the current is 0.000495. And so I need to multiply that by whatever this resistor is here, which is going to be 10,000 now. I'm going to multiply that by 10,000. And I get 4.95. Okay, which I rounded down. Okay, in this case, yeah, you know what I should do? Here's where if you round off, you can get yourself in trouble here. So I'll tell you what I'm going to do is I'm going to add on that extra sig fig. Okay. Okay. All right. So now let's think about this. So if we have a 10,000 ohm resistor, then the voltage ranges from 0.24 to 2.5, which is a range of 2.5 volts. If, on the other hand, we choose 100 ohms to be the R1 resistors, look at what that does to the range. Instead of having a range of over 2 volts, now the range, the difference between our voltages is now less than 1 volt. Okay, so the voltage is higher, but that's not really what's important. What's really important is the range. Okay, it's the spread. So if we use a 10,000 ohm resistor, the spread between the possible outputs is over 2 volts, whereas if we use a 100 ohm resistor, the spread between our outputs is now less than 1 volt. So you can see that using a 100 ohm resistor is not the best choice here. Using the 10,000 ohm resistor is much better because you want that difference to be as high as possible. Okay, so, right. Oh, well, that's okay. I forgive you, Danny, don't worry. Okay, so does everybody understand now? Your choice of that other resistor is important. You don't want to just go picking one at random. You want to do a little bit of thinking ahead of time and find out which one's going to be the best. Now, there's one other thing that's really important that we should notice. Remember when we were using our solar panel, when the burglar was there, okay, the light went down and therefore the voltage went down. Okay, so the burglar is not there. We get a lot of voltage, so we get a lot of light, so we get a lot of voltage. When the burglar comes, the light drops, so the voltage drops. So when you guys wrote your Arduino code for the solar panel one, you wrote your Arduino code so that it would set off the buzzer when it sees the voltage drop. But look what's happening here. Okay, in this case, the voltage didn't drop. In this case, the voltage went up. Okay, when the burglar is there, the voltage goes up, which is the exact opposite. So not a big deal. You guys are good at Arduino code. You can fix your code so that it makes it so that it sets off the buzzer when it sees the voltage go up rather than when it goes down. Okay, so Luke is saying it's a calculus problem, and I agree, Luke. That's a really good. If you're good at calculus, this is a wonderful example of how to do calculus, or of how to apply calculus to solve a problem. Now, I'm guessing that most of you probably don't know calculus. So what I'd recommend for most of you is just do trial and error. Where's Tristan when you need him? That's a good question. Where is Tristan anyway? Okay, so notice, again, this just is to emphasize what I said. So if there's no burglar, we have low voltage. If there is burglar, we have high voltage, which is backwards from what we did before. But that's okay, because we can just write our Arduino code appropriately. But what if we put the photoresistor in the upper one? What if instead of using the photoresistor down here too, we put it up here for R1? Would it still be the case that when the burglar comes, the voltage goes up? Or would it be the case that when the burglar comes, the voltage goes down? What do you guys think? Just toss out a couple guesses. What do you think? What's the behavior going to be like when the burglar comes if we put it up here? It goes west, okay? Okay, you're on a roll today. How about the rest of you? When the burglar comes, is the voltage going to go up or is it going to go down? I need to see some answers, guys. And answers that are not involving going west. Okay, down with a question mark, down without a question mark, east. Okay, David, I'm going to come to your house with a baseball bat and beat some sense into you. Don't worry, it'll be a Nerf baseball bat. Okay, well, tell you what, I'll just leave that out, okay? I'll leave that as a problem that I want you guys to work on. Okay. All right, so I'm not going to give out the answer here. I'm just going to toss out the question. And also, now here's a new question for you. Not only do you need to answer, will the voltage go up as down, but is it still the case that 100 ohms is going to be a poor choice? Because who knows, anything could happen, right? Maybe the fact that we moved the resistor up here, now it's possible, it's conceivable that maybe that 10,000 ohm resistor, which used to be a better choice than the 100 ohm, maybe now that might change. Maybe the 100 ohm resistor might be a better choice than 10,000 ohm resistor. Who knows? Anything could happen, right? So I don't want to answer those questions right now. I want you guys to think about those. Okay, so how are we doing for time here? Okay, so it's been about 45 minutes. I want to try and keep these sessions down to less than an hour. Okay, so what I am going to do now is I'm going to stop the recording in just a minute, but before I do, let me just tell you the plan. So that's it for today's lecture. As soon as the Zoom people process the recording, which remember it takes them about an hour to do. Okay, as soon as I get that, I will post that on Canvas. In fact, you guys will see, if you look on Canvas, you've seen that there's already a placeholder there. There's already an assignment there that says quiz and recorded session. So as soon as I get the recording, I'll put it in there, and the quiz is all ready to go. And that's your only homework, is just do the quiz. But the quiz is not going to be a simple one like what color shirt am I wearing. The quiz is going to be one where you're going to have to do problems like the ones that we've just gone over. And now, because it's going to be a more involved quiz than it was last time, I'm going to give you until next time we meet. So next time we meet will be Wednesday at 11 o'clock. So I'm going to give you until then to do the quiz. So you got 2 days to do it. So hopefully that'll be enough. So before I stop the recording, let me toss out the question or toss it open for questions. Do any of you have questions about what we've done today or anything else? I'll wait here while I look. So I need to say yay or nay. So Simon says no questions. Let's get a couple more. Marshall says no. Need a couple more. If any of you have questions, you better type yes quickly into the chat box, because otherwise, if everybody keeps saying no, then I'm going to stop the recording. And okay. All right. And David, what does that mean in English? No questions. Okay. Well, in that case, I'm going to stop the recording and I will stop the class.